Ever wonder how the universe went from just a big empty space to, well, having stuff in it?
Yeah, it's a question that keeps physicists like me up at night. I mean, we
Right.
know particles have mass, right?
Right.
Without it, you wouldn't be here. I wouldn't be here. There wouldn't even be a here.
Right. It's kind of a big deal, and the whole Higgs mechanism is supposed to explain that. But there's this one part that still feels a little fuzzy, like trying to fit a square peg into a round black hole.
I see what you did there.
Uh-huh.
But you're
Uh-huh.
right. We have this thing called the negative mass square,
Hmm.
which the standard model needs for the math to work, but it's always felt a bit like a placeholder, you know?
Okay.
Like we know something should be here, but we're not quite sure what.
Okay, so enter this paper by Harold Fritsch and Michael Spanowski, and they're basically saying, hold up, what if there's a more elegant answer? What if instead of a negative mass square, we have mixing?
Exactly. It's an intriguing idea. Imagine trying to bake a cake,
All right.
but instead of following a recipe, you just chuck a bunch of random ingredients together hoping for the best.
Okay.
That's kind of what it's like using the negative mass square in the standard model. It works,
Okay.
but it's not very satisfying.
So Fritsch and Spanowski are suggesting we need a better recipe.
Precisely. They're suggesting that instead of just one Higgs doublet, there might be two. One that's light, which we already know and love as the Higgs boson, and another that's much heavier and as yet undiscovered.
Hold on, back up a second. What's a Higgs doublet? It sounds like something you'd order at a fancy coffee shop.
Good catch. It's easy to get lost in the jargon. Think of a doublet like a pair of matched socks. You can't have one without the other.
Okay.
In this case, the doublet is a pair of fundamental fields that are linked together mathematically.
Okay, so we've got these two Higgs fields, one light, one heavy. How does that help us with the whole mass problem?
That's where the mixing comes in. Think of it like a seesaw.
Oh,
If you have one really heavy person on one side and a lighter person on the other, the heavy side goes down and the light side goes up.
So the heavy Higgs field is like the heavy person on the seesaw, and it's lending some of its weight to the lighter Higgs.
That's a great way to put it. This heavy field interacts with the lighter Higgs in a way that effectively lends it some of its properties, including its mass. And that lending action is what gives rise to the negative mass square we need in the standard model. It's like the heavy field is saying, hey, little Higgs, you need some mass. I gotcha.
Uh-huh. That's a much more satisfying explanation than just saying, well, the math works if we put a minus sign here. But how do we know if this mixing is actually happening?
That's the million-dollar question. And that's where things get really exciting. This is where our giant underground microscope comes in the Large Hadron Collider, or LHC.
Ah, yes, the LHC, where we smash tiny things together at ridiculous speeds. Picturing a demolition derby, but with protons instead of cars.
It's a bit like that. But instead of twisted metal and smoke, we're looking for fleeting signals. Whispers of new particles that might pop into existence for a fraction of a second.
So how would we even know if we created this heavy Higgs partner? It's not like it's going to wave a tiny flag and say, here I am.
Not quite. These particles are incredibly unstable, so they decay almost immediately into other particles. What we look for are the specific combinations of particles the debris left behind that would tell us, aha, a heavy Higgs particle might have decayed here.
So it's more like forensic science than demolition derby. We're analyzing the subatomic crime scene for clues.
Exactly. And Fritsch and Spanowski have given us a good idea of what to look for. They've calculated some of the properties of this hypothetical heavy Higgs, including its potential mass.
Okay, so let's say they're right, and this heavy Higgs partner exists. Finding it would be a huge deal, right? But what would it actually tell us about the universe? Besides the fact that it's even weirder than we thought.
It would be revolutionary. Right now, we think of mass as this intrinsic property of particles, something they just have. But if this mixing idea is correct, it means that mass isn't intrinsic at all, but rather an emergent property.
Emergent, like it arises from something else.
Exactly. It would mean that mass is a result of particles interacting with this Higgs field, this invisible ocean that permeates all of space. And the existence of a heavy Higgs partner would be like finding a new species of fish in that ocean.
Yeah.
It would tell us that the ecosystem is even more complex than we imagined.
Okay, I'm starting to see why this is so mind-blowing. We're not just talking about finding a new particle here. We're talking about fundamentally changing our understanding of what mass is.
You got it. And that's just the beginning. Think about the implications. If mass is emergent, could other fundamental properties of the universe, like gravity or even time, also be emergent?
Well, hold on. Now you're just getting me really existential.
Yeah,
We're diving deep into the deep dive here.
that's what we do here. But you're right. It's important to take a step back and appreciate the bigger picture. This paper, while focusing on a specific particle, has opened up a Pandora's box of possibilities.
It's like we're seeing the universe with new eyes, realizing that there are layers upon layers of complexity we're only beginning to understand.
And that's the beauty of physics. It's a never-ending quest for knowledge, a constant pushing of the boundaries of what we think we know.
It's humbling, really, but also incredibly exciting. So where do we go from here? If this paper has us questioning the very nature of mass, what other foundational principles might be up for grabs?
It's like we've been handed a treasure map, but instead of X marking the spot, it's a giant question mark. And who knows what other mysteries are waiting to be unearthed as we follow this trail.
Should we be looking for other examples of this mixing phenomenon, perhaps in other particles or forces?
That's the million-dollar question, and it's one that physicists are already pondering. This idea of mixing isn't entirely new. Remember those incredibly light particles we talked about earlier, neutrinos?
Oh, right. You were saying that physicists use a similar seesaw mechanism to explain their tiny masses.
Exactly. So if this mechanism is at play in multiple areas of physics, it begs the question, could there be a deeper connection? Could there be some underlying principle, some grand unifying theory that ties all of this together?
Now we're talking. A grand unifying theory that's the holy grail of physics, isn't it? Finding one equation to rule them all.
You could say that. And while we're not quite there yet, this mixing idea might be a piece of that puzzle. It suggests that the universe might be even more interconnected than we previously thought.
It's like realizing that all the books in the library aren't just standalone stories, but chapters in a much larger narrative.
What a fantastic analogy. And as with any good story, the more we delve into it, the more questions we uncover. We're left wondering what other hidden connections, what other elegant mechanisms are waiting to be revealed.
It's enough to make your head spin, but in a good way. This whole deep dive has left me with a sense of awe and wonder about the universe and our place in it.
And that's what it's all about, isn't it? Never losing that sense of curiosity, that drive to understand the fundamental nature of reality.
Absolutely.
Yeah.
Well, folks, there you have it. A surprisingly simple explanation for why the universe has mass and a whole universe of questions to ponder. Until next time, keep exploring, keep questioning, and keep looking up at the stars.